Engineering at a glance. Our purpose is to deliver breakthrough engineering for a better world. We help our customer controlling their processes in plant to drive efficiently and safely, providing superior cost engineering, custom engineering valves, actuation and control. This is our performance of last year, as you can see in the screen, in terms of revenue, aftermarket, the section of oil and gas. Our product is mainly on control valves, ball valves, isolation, and FCC valves. And our branding, our key branding, we have listed our companies within IMI group in the right hand of the screen. IMI Buehler, IMI CCI, IMI Fluid Kinetics, IMI Orton, and so on. If you have any question, we can answer them at the end of the session or after my presentation. Time journey of the company, IMI is established in 1800s with the history in the last century. IMI CCI joined the group in 1981. We continue acquiring some big players in the market. In 1970, in 1997, we acquired scissor valve technology in control valve, also BTJ in 2001. Up until 2006, we were only in control section. In 2006, we acquired IMI Orton, IMI Truflo, IMI Truflo Marine, which is in isolation business. And then we continue also acquiring and expanding our portfolio to cover and support our customer around the globe. Lately, we have our venture in Saudi. We established our IMI Saudi industry in 2020, this year, and the project is ongoing as planned. In terms of our people and the growth, we have a what we call a doctor program or valve doctor program, and in light of our vision, because of our product is critical, we have this program to create subject matter expert to support our customer and solve problems. Also, we have a growth accelerator program which is designed to also fast track growth within our division to put our talented colleagues at the heart of our business challenges. IMI is also taking the initiative in inclusion and diversity among our 3 divisions and in all positions. Just a quick update on our program or our venture in Saudi. We have planned to have a 20-ton lifting capacity in our plant in Saudi. To support our customer, we need to invest in high tech. So our factory will be handled 20-ton valves. We also target 56-inch size, up to 56-inch size. We will be also having ABI 6D and 6A certification. The plan is to have this facility ready by next year, early next year. Our sister company who will be supporting us is IMI CCI and IMI Truflo. With that, I will conclude my presentation. If you have any question, I will.
Thank you very much.
Sorry, I don't know if we still have the connection or I lost.
Yes, no, we hear you clearly. Thank you very much. We appreciate this brief introductory about IMI. And now we are moving on to our technical presentation, which is gonna be shared by Christian and Sekhar. So I will leave the floor to Christian. Please go ahead, present your screen.
Thank you so much, and thank you, Ahmed, as well, for your quick introduction into IMI. My name is Christian Buehler. I'm with IMI for 17 years and have been in many different functions, currently in the Director of Business Development and also part of the Retrofit 3D business unit group that we support worldwide. So pleasure to be here today in your afternoon and your evening. I'm located in the US with my friend and colleague Shekhar Sami, who has joined us at the very early hour. He is actually located in California, so it is 3:43 in his morning. So good morning, Shekhar. I hope you have a coffee ready. If the organizers could please also allow Shekhar Sami to present and share content, that would be great. He's gonna share the second half of this presentation when we go a little more into the specifications and the qualifications and the processes. But I will start off with the most interesting topic, right, which is control valves. And so we want to take a look at some of the challenges that we see in the control valve world around the globe and what the root cause of those challenges are, right? We always want to make sure we understand the technical background of why we see those challenges and what a solution might be able to address those challenges. Then obviously we're here for additive manufacturing, so we want to talk about that specifically and how additive manufacturing can be used as a great vehicle to solve industry problems and challenges. And how we do that, we call that Retrofit 3D. And then we're going to go into the DNVGL classifications and look at some of the test results that we've done internally. So we share some internal work that we've done with you on the technical side and look at the processes that we utilize to make sure a retrofit can be done in a very proper and professional manner. So that's pretty much the outline for today. And as mentioned before, please do share your questions on the chat. We'll be very happy to address them after the fact. And should we run out of time, I just want to make sure that's clear. We'll be here for you via email as well. You have the contacts from the presenters, so please do get in touch with us for any additional questions that might not be addressed during the presentation. And I will let Shekhar Sami introduce himself when he will take over his part of the presentation, but we'll jump right into the most exciting topic, which is control valves. So you might be familiar with control valves, you might not be familiar with control valves, but whenever you go to a plant, you see, either an insulated pipe or not an insulated pipe, and then you see a valve body, in that pipeline, and you see a yoke and an actuator sticking out of that pipeline. That's what you see when you look from an external perspective. But when you look at the details and you go into the valve, you see the trim in the valve that is actually doing the work. So you see a cage here on the left side picture, and on the bottom of that cage you have a seed ring and you have a plug that moves up and down, controlling the flow that you want to let down through that valve. Now, there are many different type of valves, many different type of trim designs available in the market for different applications, right? It could be a single stage where you just have the cage here and you see the seat ring on the bottom of the cage here, and you see the plug that comes down and seats at the seat right here. So you can have a design like this, or you can have multi-stages where you have not just one stage, but you have multiple stages in series, like this picture as an example. A multi-stage, multi-path trim installed in a control valve. Again, there are many different types of valve designs and valve trims, and some of the challenges that we see in the field with certain applications and valve designs is like this. Cavitation is a good example here. And when you look at the right hand picture here, you see these these damage mechanisms here, they look like a crater, right? They look like the moon, and this is really from the imploding bubbles that release very high pressure jet and impact that material right there. And there is actually no material really that can withstand cavitation. So our focus is more to eliminate cavitation because there is just no real solution from a material perspective. So this picture, I actually like this picture quite a bit because you see the damage mechanisms on several different holes here, right? So when you look at all these, you see those damages taking place, but you don't see them in between. So the question remains, why do we see cavitation taking place at some areas, and on some other areas you don't see any damages taking place? The answer is that it's actually pretty simple. Cavitation is not an exact science. Yes, we can calculate that cavitation takes place. Yes, we understand what the physics behind it, but it's not clear where exactly cavitation is going to take place. So some people try to control cavitation, but it's hard to control something that you cannot predict to 100%. So we take more the approach to say, well, we know cavitation is going to take place, so what can we do to eliminate those cavitation related impacts? Okay, another good picture is erosion that you see here on the screen. I hope you don't see trims like these. That's a pretty severe damage in a control valve, but we do see those type of damage mechanisms. And with this picture, we tried to find a picture that shows vibration and noise. And the only way we were able to do that is kind of see the controls mounted on the left side here. So this specific customer had to take the controls off the actuator mounted on a pole away from the valve, so that the vibration wasn't disturbing the overall controllability of the control valve. So there are quite a lot of issues from a noise and vibration perspective that we see and have to evaluate on a regular basis. So when you look at all these damage mechanisms that you see here on the screen, right? And actually this, I want to bring our attention to the right picture here where my mouse is circling around. This is a trim that has been damaged so severely, and that was just due to vibration. So you see these particles coming off the trim. They actually went downstream in the customer's pipe, and you can imagine that can lead to very severe downstream damage. So we certainly want to prevent that from happening. And so we're taking a step back and we're asking ourselves, so why are all these damage mechanisms taking place, and what might be the root cause of them? And when you really look, when you peel that onion, right, and you go into the details, you start to see that they all have one common denominator, which is fluid velocity. Fluid velocity is the root cause issue for all these challenges that you see in control valves. So when you look at the math behind it, you actually see that, for example, the second bullet point here, erosion. Erosion damage is a function to the velocity, the power of 2 to 4, depending on the medium. If you have liquid, it's to the power of 4. If you have more gas, it's to the power of 2. And the same with cavitation. It varies as a power to the power of 4 to 7, right, of velocity. So just imagine if you can reduce that velocity by a certain amount, your impact to the overall system, to the valve and the system itself, is going to reduce to a much larger. Obviously, the same goes for noise and vibration and corrosion as well. So there are many damage mechanisms that are directly associated with the fluid medium control velocity that is going through the valve. So maybe we have to talk a little bit more about the principle of velocity and how velocity is being generated in a control valve. So again, this picture, you saw this picture in the earlier slide here. So you have the cage, you have the seat ring, and you have the plug that is moving up and down. And so, at the inlet of any control valve, you have the upstream pressure, right? That is the system pressure that is being applied to the control valve. And then at the outlet of the valve, you have P2, which would be the outlet pressure, which is determined by your required system pressure at at your downstream system. So the control valve really doesn't define P2. The control valve will have to handle or dissipate that pressure drop from your inlet and outlet pressure in a way without applying any damage to the overall trim and system. So depending on the type of trim again, and here you just have a few holes, and those holes, they have a certain amount of area. So if you calculate all these holes and area up, and you have a certain mass flow that is being pushed through the valve, you can calculate the velocity through that trim set. And so really that's where we're focusing on. So the velocities here at the trim exit, and then obviously through the seat bore and right after the seat. Those are the velocity areas, or the core areas that we look into to make sure we understand what is actually happening in a control valve. And when you think of this, upstream pressure, you can think of it like a waterfall, right? This is actually a beautiful picture of the Niagara Falls in the United States. This is actually on the Canadian side. And when you think of all this energy, right, that is being pushed against that control valve, you can think of it as potential energy that is being transformed into kinetic energy and let down like a waterfall. And once it hits the ground, it will impact that ground, right? It will start to erode the bottom and create a lake below that waterfall. So how can we have the same velocity, or the same potential and kinetic energy, and let it down in a way without creating that damage mechanisms on the bottom? We can do this via step effect. So this is a picture of kind of a fish ladder here, where the fish could just jump upstream, and you see here it's the same amount of energy that is being let down, but it's being broken down in steps, and it will never get to those high velocities that you would see with just a single stage drop over the cliff. So you see here, when you look at the water, you see the clear water on top, right? And you see how it starts to create eddies, and how the velocity slows down, right? It accelerates again, and it falls, and it slows down again. So it never reaches those high velocities, and you won't see that damage mechanisms. So we might have to ask ourselves, so what velocities are we talking about in control valves? What is a good velocity and what might not be a good velocity? And when we look at the different installations worldwide, we see quite a large range of velocities. And if you have been involved in pipe designs or pipe engineering, I'm pretty sure you're well aware of the very stringent requirements to keep the pipe velocity very low. So in liquid services, it's not uncommon to see 3 to 5 meter per second velocities in pipelines. Now we sometimes see in control valves between 100 and 165 meter per second. That is a very, very high velocity going through the valve. And you would obviously never allow such velocities in your pipeline, because you would know it would destroy your plant. So the question really is, what is a good guideline, or what should we adhere to? And the ISA has a very, very good guideline that we consider in our designs, which they state that we should be below 30 meter per second for liquid applications. And in gas services, obviously, the velocities can be higher because your density is different. We always have to consider the density of the medium, so we can go with a higher velocity, but we more look at the kinetic energy or the dynamic pressure. And the ISA guideline again states that we should stay below a 70 psi of dynamic pressure. And so these are the design criteria that we adhere to that are within the ISA guidelines. Now, again, if you look at a trim and you see these holes and the high velocity jets that are being generated here, how can we break them down or slow these velocities down? And we do this with our drag design that you see here on the left side. So when you look at a drag, that's just one sector here. When you look at our drag this stack, you see the medium going in from this side, and you see it looks like a labyrinth, right? So we take multiple right angle turns and force that medium, whether it's a liquid or a gas, force that medium to slow down. We will not allow that medium to achieve high velocities that we know are directly associated with all the damaging mechanisms that we've seen before. And again, if you have been involved in pipe designs, you know that a 90-degree elbow in a pipeline is taking the maximum amount of system pressure loss. So you certainly want to stay away from that if you can in a pipe design, but within a control valve, you want to dissipate that energy, and therefore you want to apply enough stages to kill that kinetic energy in a safe and effective way. And so there are many different designs available. Obviously, you can do over the plug flow. When we say over the plug flow, we mean coming with a flow here from the right side and going over the plug, right through that disc stack, over the plug, through the seat, and then out. And if we say under the plug, we mean we could come from the left side and we go under the seat, under the disc stack, plug, and then go out that way. So obviously we can flow in both directions, and we can characterize that disc stack to the specific application. So each layer can be designed according to the operating conditions that you have and to the application. This can be very powerful if you have different pressure drops as you operate your plant, where you could have 30 to 40 turns maybe on the bottom and maybe less turns as you increase your flow. So this really helps to customize a system solution for your operation. Now, when you look at a control valve, and we've seen all these damaging mechanisms that we want to address, I think we clearly established that the trim itself is where all these damage mechanisms take place. So when you can have a valve body, and a valve body can be a challenge, and an actuator can have some challenges as well. But I would say in most cases, the damage mechanisms take place right in the control valve. It's being generated and it's being impacted the trim itself. So we're asking ourselves, how can we address all these issues? And what if we could eliminate them all by just replacing the trim in the control valve? Right? No need to address the valve body or actuator, just the trim itself. Now, if you have a welded valve, you will have to, when you have to replace that complete valve, you will have to take that valve out of line, and you require a crane to do so. You might not need a crane if you just do maintenance in the valve in line. If you have a flanged valve, depending on the processes, you might have to take the valve out of line, you might not, but a crane might be required for that as well. Now, again, if you have a welded valve, obviously you would have to cut the valve out if you have to replace it. If you have a flanged valve and the face-to-face dimensions change, you will still have to do some of the pipe work, which can be associated with a high cost as well. So if you just address the issues in the trim, you can eliminate any cutting, you can eliminate any welding, you can eliminate any NDE that is associated with the welding procedure, and then a post-weld heat treatment as well. And again, it's all associated with a pretty high cost of installation. And such a solution that addresses the root cause issue within the valve without really considering the valve body or actuator for replacement is giving a direct cost benefit to the plant. And so such replacement of a valve trim is retrofit. And you might have heard of that name. I just want to make sure it's clear. A retrofit is not a replication of what is in the control valve. A retrofit is an upgrade with a highly engineered trim solution that is being implemented into the same control valve. Now, we have been in the retrofit business for over 30 years. We have done many different retrofits in many different applications around the globe. And here you see a traditionally manufactured disc stack. And this disc stack probably has about 20 stages. And just imagine if you have a cage with just a drilled hole, you don't need as much area to fit all these holes. But if you have 20 stages, you need a little bit more metal or material to fit all these stages. So in the past, very often we had to look at the diameter and see if that diameter would fit into a given control valve you have installed in your system. And the same applies to the height. We sometimes required more stroke to accommodate all the system requirements, which very often led to a replacement on the bonnet and on the actuator as well. So you would end up with just the valve body in line, which can be a good solution. But over time, you realize that there are better solutions that we can look into. And this really brings us to the topic of additive manufacturing. Additive manufacturing allows us to manufacture a disc stack that is equal or better to the current disc stacks, but is saving us 40% in volume, meaning we now can design a solution that addresses the core issues that can be installed in any given cage-guided control valves without the requirement of changing any bonnets or actuators. So this is a huge benefit, and really additive manufacturing allowed us to do that. And so let's quickly talk about what additive manufacturing is, or what additive manufacturing is not. Additive manufacturing is not subtractive manufacturing. So you don't have a given, forged bar or a cast material where you shave off material to create a three-dimensional part that is installed in your system. Additive manufacturing, as the name it already kind of alludes to, it's you add up, you build up, you add up materials, so you build a part from scratch. You don't take anything off. And you might have heard of 3D printing. So this is nothing different than 3D printing with metal. And there are different additive manufacturing technologies available. One of the most known is the laser power bed here that you see on the left side. And another one that we utilize quite often is the binder jet. There are some other technologies out there like the electrobeam and others that are in evaluation and used for certain processes. From a material perspective, there are quite a few materials already available. So Inconel 718 and 625 is available. The 316 stainless steel materials are available. Titanium, aluminum, and Stellite 6 is available. And there is a 17% cobalt tungsten carbide material available, but the higher performing grades are not yet available. They're still in development. And so is Stellite 720. So there's still a lot of development going on for additional materials in the marketplace, but there is a wide range already available. The sizes and the speeds of the 3D printing machines are in very quick development as well. We are manufacturing up to 11 inches in size. But we are looking at going larger here up to 600 millimeters. So 290 millimeters is very common, and the 600 millimeters are in qualification. So there are bigger and bigger machines coming into the marketplace. We see two lasers to be the most common one. There are 4 lasers as well, which is in qualification. In the qualification phase with us as well. Now, there are many industries that have been embracing the additive manufacturing, like the submarine, like the space industry. And this is a picture I found, which is quite interesting. This is actually a rocket that was printed via additive manufacturing. And the fuel that was used on this test bed here, this is solid fuel, and it was also printed via additive manufacturing. Now, the space program is looking to reduce the lead times from years to months by utilizing the benefits of manufacturing. And you might have seen, some of the news in the medical field. The medical industry is utilizing additive manufacturing for printing skins, and also they're looking at printing organs as well. So quite an interesting development to follow. And if you have a gas or a steam turbine in your plant, you might have seen the turbine blades, being manufactured via additive manufacturing as well. And IMI, has not been, is not new to additive manufacturing. It has been around for a while, and we actually started our additive manufacturing journey 12 years ago. And we certainly, learned a lot of lessons in the first few years, how to do it right to get the most benefit out of additive manufacturing. And we have quite a lot of installed base, since the beginning of our journey with additive manufacturing. That's in the oil and gas and in the power sector. And so some of the benefits that we see by utilizing additive manufacturing is on the simplification and consolidation, right? Instead of having multiple parts, put them all together into one single item, that eliminates a lot of process steps and helps us on the lead time. But one of the real huge benefits from a system perspective is on the increased accuracy, which allows us to have a higher turndown. And you might ask yourself, so why would that help a plant? What is the impact of a plant? I want to share with you a test that we did with this is a power plant in the Americas. And when you look at the left picture here, this is the steam temperature from the steam going to a steam turbine after spray water has been injected into steam flow. So just imagine you have your pipe and you have steam coming from the boiler and going towards the steam turbine, and we have to inject water to control that temperature to a very accurate temperature limit to make sure that we don't negatively impact the steam turbine. Every steam turbine has a certain set point temperature, and if you cross that set point temperature, the plant will have to shut down. So every plant will want to make sure that the steam temperature is below that set point temperature. Just to kind of give you the outline of this application here. And so what you see on the left side here is, the steam temperature fluctuation, which you see Fahrenheit. So you can imagine this plant had to reduce the outlet temperature to include a little bit of a safety gap to make sure that the plant doesn't have to shut down. And when we installed our additively manufactured this stack and trim solution, you see here we were able to bring that down degrees. Now you can imagine that the benefit to this plant, where it did not only have a huge benefit to the overall material stress, the plant was able to increase the outlet temperature to the steam turbine and generate a bigger output with a higher revenue. So that's just one of the benefits that we've seen by utilizing additive manufacturing. But I would like to share just a few case studies on how such an installation could look like. And this is actually a valve in the oil and gas. In an oil and gas installation, it's the condensate blowdown valve. It's a 2-inch NC300 valve with a 3/8 inch of a trim. And this specific valve had some challenges where the bonnet was being negatively impacted, and the trim did not last as long as required. We were asked to look into a potential retrofit solution. And so we actually approached this issue with a twofold solution. The first one was, this was a flanged valve. So we were able to change the flow direction from under the plug flow to over the plug flow so that the bonnet is no longer negatively impacted. And then to protect the valve body from this flashing service, we included a flow diverter here. We call that a seat basket on the bottom. So when you imagine you have your flow going through the seat here, and it's being diverted away from the valve body with a 9-degree elbow here, that is forcing the medium to go towards the outlet of the valve. So we eliminated the impact of the bonnet, we protect the valve body from negative impact, and we included up to 16 stages of drag in this trim to control that velocity at any given stage in that control valve. So that's just one way on how it can be addressed. And obviously we were at the same time looking at the flow conditions, and we're adjusting the capacities to make sure that this plant sees the maximum benefits from the new trim. This is an example of a little bit of a larger disc stack. This is actually a disc stack that went into a compressor and a surge application. The material was Inconel 718, and it had a pressure drop from 213 down to 82 bar. So quite a substantial pressure drop, and close to 7-inch in OD, and we included 10 stages, and we were able to deliver this stack to this specific customer in 4 weeks time. So quite a nice. It's not the biggest one that we manufactured, but it's one of the larger trim sets that you see here, the disc stack that you see here on the screen. And maybe another example here from a power side, from our coal power plant. And the application is a spray water valve where it injects water into the steam flow, similar to what I described in the previous slide. And what you see here on the left side, you see the original trim. This is a little bit of an interesting design. It's a combination of a seat, which you see here, and the cage. So the medium is being pushed through the cage, through the seat down here into the valve. So it's a combined trim solution. And you see the thread here. So this trim is actually threaded into the valve body, and it's not compressed with a bonnet from top down, but it's just screwed into the valve body. And so when we were approached by this client to see what we could do to help to address their leakage, we wanted to provide a solution that does not only address the velocity related impact that was leakage in this case with flashing and cavitation, but we wanted to make sure that the valve body and bonnet did not require any machining. So we designed a drag disc stack here with 12 stages, and you see the seat here. So we made a disc stack seat combination that had the same thread applied to it. So this customer was able to take out the old trim and just put the new trim in, screw it into the valve body, and you see the slot here on top that allowed this customer to tighten it into the valve body and install the plug assembly and put the valve back together and operate successfully. So that's a little bit on the higher pressure side. So it's a 1,500 pound class valve. Actually increased the capacity slightly in this valve, and again we applied 3 times more stages than what the original design had to enhance that system performance. Maybe another quick example here from a combined cycle plant where we were able to address 2 different applications. One is the fuel gas heater condensation valve. This application really had a huge challenge on the vibration and noise side, and we were able to address that by redesigning the trim, and we only had to redesign part of the trim. It was a unique solution, and we eliminated all the noise issues in that valve. And on the right side here, you see some of the parts being printed here. This is the disc stack, and you see the plug assembly here on the top. This is a feed water recirculation valve with quite a substantial pressure drop. And it was a 4-inch valve with a capacity of 23, and we were able to retrofit a couple of those valves with a 2.5-inch trim, 3-inch stroke, and we adjusted the capacity as well to the demands of this system and how the plant is actually operating the valve. So we were able to address that, and we are actually looking at additional applications in this plant as well. So and again, when you look at a control valve, right? So the only thing we're replacing is the trim within the valve. So we don't want to replace any of the top works or the valve body itself. So maybe before I hand it over to Sheikh or Sami, I want to show you another very unique study that we've done. This customer wasn't sure if the conditions on the data sheets are still accurate. So they sent us their DCS historian, so the PI data, and we were able to have 65,000 different operating cases and put it in a graph to visualize it a bit better for ourselves and the customer. And we're able to not only design a trim solution that includes a disc stack with 24 stages, but we then went another step and said, okay, we see this application will flash. Physics is physics, so this application will flash, but we have to protect the valve trim from the flashing impact, and therefore want to add another stage of protection, which we did with a seat basket that included another 8 stages of drag. So it's a combination of the disc stack and then the seat basket. So altogether you have 32 stages in this solution. And when you look at how this looks like in real life here, you see here the printed version of this drag seat basket. So that's just another very interesting case study, an interesting solution that we were able to work with a customer of ours. So with that, I'd like to hand it over to Shaker Sammy, and Shaker, I hope you can take over the screen.
Thank you very much. My name is Shaker Sammy. I am the Global Director for Engineering Standards with IMI CCI. Can you hear me?
Yes, very clear.
And clear, yes.
Okay, I just want to make sure I share my screen.
It's on.
Okay, you can see my screen also. Okay, very good. Thank you. Salam alaikum and good afternoon. Thank you for joining us. And I'm going to focus more on the retrofit 3D part of this. There is a lot of activity in the industry on bringing up standards to ensure that, especially for oil and gas applications, that there are robust methods of producing this. API is one of them. DNVGL is one of them. And I'm on both the committees for these standards. And then I'm also going to share with you some of the material testing that we have done and so forth. And then I will finally talk about what are the 8 steps that are required to have a successful retrofit. Let me see. I'm not able to change my slides.
Yeah, I think I'm still sharing, Sam, if you want to share your screen.
Okay. Okay, let's see here.
There you go.
I'm still not able to share for some reason.
We see your screen.
You see my screen?
I see,
okay.
Yeah, we see your screen,
okay.
But not the presentation.
I was not able to advance the slides. Okay, there we go now. Okay. With DNVGL, there are 3 levels of parts. It's called AMC part. Level 1 would just be a simple part which doesn't require any kind of qualification. It doesn't see much loads on it. To the highest level, which is AMC3, which is extremely critical part. There's a lot of dynamic loads. It's a pressure boundary part. And
excuse me for interruption, but what screen we are looking at right now to make sure we are on the right screen?
Can you say drag stack AMC level?
No, can you minimize the team screen so we can see the PowerPoint, please?
I see only initials and...
Yeah, we only see the team's screen. We don't see the PowerPoint itself.
Christian, can you just go ahead and share that, your screen? Let's do it this way.
Absolutely, no problem. It is on the screen. Just let me know when to move to the next one.
Okay, let's move to the next one.
Okay.
Okay, so so there is an intermediate level called AMC2, which is something in between, which does not have much of stresses on it, yet it provides you a good level of assurance of quality that you can use this part in an application. Let's go to the next one, please. Okay, so here you see what you see here is a disk stack that's been printed. And then if you look in the middle of the disk stack, way in the bottom, you can see there are 3 test coupons that are printed with it. So with every time we print a part, we also print some test coupons with it, which what we do is we send them out for tensile testing, We look for elongation, and a lot of times for oil and gas application, we also do impact testing for these, Sharpie impact testing. Next, please. Okay, so let's look at some test results. There we go. Okay, so like I said, this particular distract from the presentation that Christian gave, you see that it is basically under a lot of compressive load. So what we do is we have done extensive testing on these distracts by simulating that compression load on it and see if it is in the linear elastic range when it comes to what we predict it should be. And you can see the test results there that shows that it is indeed in a linear elastic region, and there's no plastic deformation that was formed. So we know that this distract was printed correctly. Next one. Okay, so this is a very important testing that we did. So we had 3 different machines with our vendor, and we said, okay, because there's a lot of dynamic applications that we are looking at, and in which we wanted to do basically a fatigue test. Okay, the bottom line on the left, you will see there's a separate line all by itself. That is the aerospace specification. There's Airbus actually that is their fatigue test. And then we also have on the top these colored lines that we printed these on 3 different machines, and we went through more than 1 million cycles for fatigue and looked at the alternating stress. So we do see that, if you print the 3D parts correctly and heat treat them well, you can get properties that are basically superior to what you have with wrought materials. Next slide. Okay, this is another interesting test that we did, and let me give you some background. So when you 3D print any parts with laser, we know that the properties are not supposed to be uniform. So there is some anisotropy when it comes to the properties. So if you print a part which is horizontal versus vertical, you should see variations in tensile stress and yield stress of those parts and so forth. And also when you print it at a 45 degrees, it's somewhere in between. So here in this graph, you see that the blue bars are the ultimate stress and the orange bars are the yield stress. And the 2 horizontal lines on the top, one is the gray, which is for the actual yield stress per aerospace material spec 5664, and the ultimate stress is shown with a black line. And you can see that when you print this correctly with the right parameters, that you can meet and exceed any of the material specs that are out there. And by the way, most of the heat treat for Inconel material, this is what this one is, comes from the AMS spec. Next slide. Okay, here's a typical additive manufacturing over many, many tests that we have done. We have found that the properties are shown here. So the tensile strength is normally 1241. So this is around 1240. So it's very, very close. And then the yield stress, you can notice, is slightly higher. It's about 1200 megapascals compared to 1034, slightly higher. The elongation is actually extremely good. It's about 27% elongation. And the hardness, which is really a function of further heat treat that you can do, is greater than 30. The surface roughness also is slightly different depending upon how you print it. If you have a roof that you're printing, that has got slightly higher surface finish, which is about 19 micrometers. And then if you have something that is vertical, then you get about 6.3. Next slide. Okay, so the retrofit process, we have done a lot of retrofits like Christine had shown in his presentation, but we do go through a mental list and we write this down when we are talking with you about, retrofitting a particular valve that is there in your plant. Okay, so a lot of times, obviously, when you're coming and asking us to retrofit a valve, it is an issue and it's probably an important valve in your plant. So we need to understand that how our retrofit will affect your plant, if any, or improve the performance of your plant as required. Okay, so we we want to know, Christian did show you some of the properties and data that we get from you, and we analyze that data. Okay, next slide. Okay, so there's an 8-step process, which I'm going to go through in the subsequent slides, but you can see right here that we start off by reviewing the existing valve. We review the data sheets that you have for the existing valve, but we also go back and review the DCS data, which actually tells a lot of story. What we have found is that how the valve was designed with the 3 or 4 service conditions versus your DCS data that actually shows how it is being used in the plant reveals a lot of what we see. And very rarely do we see that those 3 conditions are representative of exactly how we are using the current valve in the plant. And then we also we go through measurement of the parts and the installation of the parts and the quality aspects. Next slide. Okay, so here you can see here, we typically get the drawings from you, the data sheet from you, and also the parts list, because that also tells us a little bit about, which parts from the drawing we need to replace and what they are actually called. Because a lot of times we are making parts that mate with existing parts that you have in the plant on the current valve, so we need to be aware of how that will impact. Okay. So here is an installation picture. We generally get that information for informational purposes as to how it's installed in the plants. But more importantly, we actually look at the damaged parts. You can send us a picture of that with what kind of damage is there. And sometimes when you have fractures, we would request that you send us some pictures with a zoom in so that we can actually look at the structure of the failure and we can understand a lot about how it failed. Okay, next one. Okay, so a lot of times, most of these applications that we see, you also need to understand, how this application works. So that's where a detailed experience in that application and application knowledge is important. And the last one bullet point is IWB means it worked before, and IDWB means it did not work before. So we also go back on our experience, and a lot of times, service conditions alone don't tell you the whole story. You also look at the past installations where we have success, and we have that tribal knowledge to guide what we should do and what we should not do. Next one. Okay, so we talked a little bit about reviewing the DCS data. On the right side, you can see the DCS data is extremely important, and typically what they do is they send us the upstream, downstream pressures, the flow rates, the temperatures, and the valve position of the current valve. And using that information, we can plot, and you can send us tens of thousands of data points, and we have a program that actually takes that and plots that data does calculations for us in many different ways, in which it'll help us understand how this is used. We also request that you have a timestamp in there so we kind of know how long a valve dwells in that particular position. Next one. Okay, so once we have that information, we analyze that, we will send you a proposal and give you a feedback as to what we think is the issue with the current valve and what we think should be the solution. So we get the feedback from you as to what you think about the solution. Are there any other concerns that you have with the solution we have proposed, or you think there's some other issues that we have not considered? This is the time for a feedback session from you for us to understand how to tweak our solution to meet your needs. Next slide. Oh, then the next step after that would be to measure the existing parts. But remember, we are trying to replace only the trim parts so that all other parts in your valve can be kept the same. We only want to replace those 3-4 parts, which are the trim parts. We do not want to change anything, or we don't want to machine anything in your existing valve. We want to keep all the actuation and everything exactly the way it is. So to do that, what we do is we take the existing parts. If we have them in your warehouse, we can come there and measure the parts or if you wish to measure them, that is fine also. But typically we like to measure them because we do know which are the critical surfaces and which are the critical tolerances that are there for these trim parts. So we have some domain knowledge that kind of helps us take the right way of measuring these parts by even stacking them in a particular way to measure them. We do not need for you to send the parts to us. We can send somebody there. And then we talk to you about if there are any special quality requirements, any special documentation you require from us, so that we can make sure we collect all the data for you so we can send you the doc package. But internally, we have a stringent quality assurance program to ensure that the parts we have printed are good from all the test data, and we design them to the industry standards and applicable codes. Okay, next slide. And finally, the installation. What we do is in the factory, we stack up all these parts. We do complete dimensional check against what the measurements are to ensure that there are no issues. So every kit that we send you is independently stacked up and measured and looked at. And then we can have personnel that can come into the plant and show you how to put this together. Maybe the first few retrofits that we do on your plant valves, we can come in and do. And as you gain experience, maybe we can do it remotely also if necessary to guide you through the installation of the parts. Typically, the way the parts are designed is that you really don't need any special tools. You don't need any special instructions. If you have crew that really understand how to put valves together, they should be able to put this together. Next slide, please. So thank you very much for listening to this presentation. We are available, and I did see a lot of questions that have popped up. We do have a retrofit website called retrofit3d.com, or you can see that Q code that's there. And also we have our email address, and you also have a contact address of our local people in Saudi that actually will interact with you and get that information to you to us. We work very quickly to come up with practical solutions for your problem. Thank you very much.
Thank you, Sami and Christian, for the very informative session. Now we'll open the floor for Q&A session. So I will read the question for you, either Sami or Christian. Please feel free to answer the question. The first question is, in case a line that runs with the debris, what will happen if the debris start to clog from the bath in the cage?
Yeah, excellent question. So, what you have seen here is that you've seen some smaller passages that are typically used with clean services. But as we know in the oil and gas field, there could be debris that come through. So as we are able to print larger size passages that actually allow the debris to pass through. So what we request from you is tell us what type of debris it is. If it's sand, we need to know that, obviously, because of erosion issues. But if there are other size debris, if you have done a debris study and you know what are the typical sizes that you could see and the size distribution, if you have that information, or you can give us the maximum size, we can actually design and print trim parts that are larger in size, which will allow these particles to snake through the disc stack and pass through that.
Perfect.
And maybe add to this, just if I may, and maybe I can go back in the presentation slides a few. We have, our control valves are installed in oil and gas applications like choke valves, where you have a sand, you have rocks, you have water and oil and gases coming through at the same time. So we apply the same designs for those applications, and you can imagine there are quite large particles in there. So we can, and I would like to go back just to one picture to show you how we protect the trim itself from clogging up as well. I think I passed it. I don't see it right now, but
no, I didn't see it, Christian.
Yeah, so what I'd like to share with you, just to make sure you understand, is that our inlets on the disc stacks are the smallest area. So as you let the medium down throughout a trim, the area is only going to increase in size. So meaning anything that is being passed through the inlet is gonna be allowed to go through the trim without any problems. Okay, so we don't have any contractions within the trim itself.
All right, clear.
Yeah.
Moving on to second question. Dry design can be used for surfaces having sand particles.
Yes, we have on the choke valves. So in that case, what we do is, Christine touched upon the binder jet technology. So what we have done is we can, if it's sand alone, a lot of times we can, and depending upon how much sand, one is the tungsten carbide. We can 3D print tungsten carbide also, to do that. But however, that one is still in development stages because the cobalt content is fairly high. They've actually come down to about 12%, and now they're working towards a goal of 7% binder, so that the remaining is all tungsten carbide. So that, I think, is a matter of time when it shows up. Maybe in a year they will have that. But we are able to also print stellite and tungsten carbide, because if you have those particles, yes, that's what you need, and we have done that.
All right. Thank you, Sam. So moving on to the third question. As an end user and not a control valve specialist, I keep hearing from all competitors claiming they have the best control design for my operation. Now, in your opinion and based on your experience, what should I, as an end user, be looking for?
Yeah, it's an excellent question. And maybe I can address part of it. And Sam, if you want to add on to that, that's great. So the one thing that any control valve data sheet does not show is the velocities. And that's one of the core, what we showed in the beginning is one of the core issues that we see in control valve. It's the trim exit velocity. You might ask your valve vendor, what the outlet and inlet velocities are in the valve, and they might give you that information, but that's not the velocity that's actually taking place in your trim. So what you really want to take a look at is, what is my velocity profile at the trim exit at any given stage of my control valve? What are those velocities, and compare them to other control valves in the industry. And that will be a very, very good indication of it. Another indication obviously would be, the experience in the application. The application itself is not reflected on a data sheet either. So when you look at a data sheet, everything might look just fine, right? Because a lot of those things that need to be known are not necessarily reflected on a data sheet. So think about the experience and references for this application besides the control valve velocity profile. That's probably one of the key factors. And there are some designs that are just trying to cut corners. And you have to look into that and make sure that you have something that brings you the controllability that you require for it as well.
Okay. Let me ask a question that is coming down that I did see. You said, what is this ISA guideline? There is a book that is published by ISA. It's called Control Valves, Practical Guides for Measurement and Control. In that book, it's about $188. You can buy that book, still available from ISA, or, we have actually reprinted portions of that with permission from ISA as a little booklet that we have in PDF form that also we can send you. But that has got, specifications, and we have seen increasingly a lot of ENC vendors and include that requirements in there for trim exit velocity and what are good practices that you should do when you write a specification for control valves. So that also is an important thing.
Perfect. So the next question is basically, does your design consider improve acoustic induced vibration or flow induced vibration?
Yes. So, one of the things that we look at is the velocity. So, this is the important thing. So if you have a pressure drop across a control valve, that energy, if you look at that energy and you calculate how many horsepower or kilojoules that you have in that energy, about 2% of that energy is available for vibration. So if you reduce that velocity, what happens is the jet exit energy also comes down. So 2% of a reduced energy is even less energy that's required, that is available to excite all the parts. Second thing is also the piping configuration. So it's a lot of times plants we have seen, use eccentric reducers in front of control valves that induce, skewed flow profile, or they have sudden expansions after control valves. The outlet may be 20 inch and then the pipeline may be 48 inch, and then there's no way of controlling the expansion. Those things all cause problems. And there are solutions that we can provide upstream and downstream of the valve to fix those. So that's where the problem comes in. So a lot of times it's velocity, and it's also the velocity profile where there's excessive flow separation that causes these acoustic and vibration problems.
And there is a follow-up question actually that came on that as well, and from an environmentally unfriendly high noise level perspective. The question is, at what level should we be worried about the damage in the valve and the components? That's an excellent question, because a lot of, again, the data sheets, they might state 85 dBA at 3 feet or at 1 meter from the valve, and if it's a steam application, for example, you might have insulation on that pipe, and that will take some of that noise level off from where you stand compared to the control valve. So if you have 85, for example, in a steam application, you might see 100 to 105 dBA in the control valve itself. So think about what's happening within the control valve. So depending on the service, and again, it all depends what the application is and the mediums are, but anything above 90, I would start to look into a little bit more details and understand what's actually happening, and should we be worried about them. We'll be happy to assist you with such an evaluation.
Yeah, so the typical requirement that you have 85 to maybe 90 dBA, you do not want to exceed that, because the moment you start exceeding that, maybe on small valves you may go even up to 95 and you will be okay, because the stiffness of the pipe and the supports are larger compared to the flow area. But when you go to larger pipelines, actually you really want to reduce that even further, because if you look at the section modulus of the pipe in comparison to the flow area and the energy flowing through it, larger pipes are susceptible to a lot more vibration and failure of supports and those issues. So you really need to bring down those velocities even further. For long transmission lines, by the way, we have done projects where their requirements are around 60 to 65 decibels requirement, because they are close to homes or anything like that, where there's a noise issue. So we have done valves with a lot more stages to bring those noise levels down to even those levels.
Okay, cool. So the other question is talking about the retrofit. What kind of warranty we get as an end user? Yeah,
that's a great question, and that we can obviously talk about the details, but we always stand behind our solutions. So we provide our solution, our trim kit with 12 or 18. So usually it's 12 months after installation or 18 months after shipment, whatever comes first. But again, we can have a discussion if you have any detailed concerns or requirements on that front. But in general, we always stand behind our solutions, and our goal is to make the system better, give you an improvement, and eliminate the issues. That's what we have been doing for the last 50 plus years, and that's what we're focusing in the future as well.
Perfect. Now, is there any limitation for selecting the materials to be used? For example, can tungsten carbide be used?
Yeah, that's a great question. Sammy, you want to address it?
Yes. So right that we are printing is tungsten carbide, stellite, and Inconel. And the reason we picked, and you may wonder why are you picking Inconel? That's simply because Inconel powders are relatively cheaper, because they're used a tremendous amount in aerospace industries, and there's an enormous amount of experience across the board. If you really go and look at all the research papers in additive manufacturing, you will see Inconel and titanium are there. The machines are optimized for that. And the good thing is with Inconel is you're getting a better material because, when you print a part, if you print a 316 or Inconel, the cost difference is not that enormous because it is the machine time that's expensive. They spend $1 million to put a machine there, and they do charge you by the hour how long it takes to print that part. So the powder cost for Inconel has come down dramatically, and they're printing a lot more of that. And when you have machines that print Inconel, they don't suddenly change that and put 316 inside it because there's contamination issues. So they do print 316, and we stuck with that because with Inconel also you get much better properties, strength-wise, erosion-wise, and many different ways. It is much more superior. So that's the reason why we print a lot of Inconel 718. But we have also done stellite and tungsten carbide, obviously.
Yes, on the tungsten carbide, maybe just to add to that, depending on the level and the levels that we use for tungsten carbide, the powder is not yet developed, so that's still in development phase in terms of the very, very high quality tungsten carbide. I think we showed that in the previous slide. So, talk to us about your requirements, and then we can look at the details, please.
Perfect. Now I have another question which is directly related to the material. Now, is there any shape limitations such as round edges or sharp corners?
Yes, that's a good question. Typically, when we print it, it may print as a sharp corner, but again, after you print it, you do have to machine some of the sliding surfaces. Okay, so when you print a part, you can't suddenly take that part unless it's a bracket or something. You can use it right away. But if you are talking about trim parts, we do have to machine the ID and the end faces of that part. But it's very little material that we take off. Maybe 0.5 millimeter is taken off from the surface to get a smooth surface. So I hope that answers the question.
All right. So other question. We're running out of time, but I think we will have room for 1 or 2 questions. Can we use 2 control valves in parallel to handle high pressure drop? And if yes, is it preferred?
Yeah, let me answer that question. Well, there's no need to have 2 control valves because whatever pressure drop that you have, we can take that in 1 valve. So we have done, 300 bar pressure drop. Obviously, we have done, API, 10,000 or 15,000 valves, with high pressure drops. We have done that. So there's no need to actually use 2 valves because that adds cost and space requirements in your plant. So there's no need to do that.
Maybe add to Shekhar's comment there. Think about your controllability, right? If you have 2 valves in series, to control your system properly is a lot more complicated than if you just have 1 valve, and that takes care of your operation. So whatever you do with your first valve, the second valve will have to compensate and work very nicely along the first valve. So that can present some challenges. So maybe we can support the simplification of the overall system by taking the whole pressure drop through 1 valve.
Right. And also, I think the question actually probably alluded to the fact that you may have a wide rangeability requirement. With our designs, we can get a lot more higher rangeability because all you're doing is when you're opening with the plug, when you're moving, you're opening up discrete flow passages. So there is no loss of control. So we do get a much higher rangeability out of our valves. Like, typically I would say 100:1 is not a problem for us.
Okay. Last question is, do you use CFD modeling and analysis in your design of retrofitting solutions?
Yes, we do, but we also do flow test. There's a reason why ISA or IEC specs do not allow you to just use CFD for CV tests, is because CFD can get you close enough, but it really is not 100% accurate. So what we have done is we have benchmarked all of our designs using CFD, but then we also do flow test to get the final numbers.
Yeah, that's right. And I just saw, maybe a final question quickly here that we can address, what our track record is from additive manufacturing. We mentioned that we've started that 12 years ago. So we have over 500 parts already installed in many different applications, and we actually see fantastic performance. from any of those parts. Not that I'm aware of, we don't have any warranty claims on any of the additive manufacturing solutions that we have installed.
All right, by that we conclude the Q&A sessions due to time limitation, and I will ask my attendees, please feel free to contact IMI for any further question or clarification, where they are already sharing their contact information. Now, moving on to our next part, which is raffles. I have Abu Abdurrahman. Saad, can you please, are you with us?
Yeah, I can hear you. I can hear you loud and clear.
Perfect. So,
something is spinning. Yeah, I can see your screen.
And I think everyone should be ready now.
Tell me whenever to start. على ما قال to start spinning.
Ready
then
to start.
Spin the wheel, أجل. Today we will be having 5 winners here. Can you hear me all?
Yes.
We should have 5 winners today. ما شاء الله. دكتور جمال. ما شاء الله.
All right. So we will, if you can just contact us on privately, Dr. Jamal, we will share the voucher detail. Our voucher for today is going to be from Amazon, so more flexibility for everyone. We're moving to next.
Bismillah, spin again. ما شاء الله. اللي مسجل as a guest, I don't think we can. ولا لا, we don't know who's the guest here.
We don't know the guest, so everyone can claim they are our guest. We remove the guest. Spin it again.
Spin again.
I'm sorry, Mr. Guest, but please register with your name later on.
ما شاء الله.
صادق البويدي. Congratulations.
صادق البويدي. ما شاء الله. You are taking note of the names, right? I'm assuming.
Yeah.
Okay, good. طيب, we have 3 to go. Bismillah. Spin it. ما شاء الله. عبد الرحمن النشوي. عبد الرحمن النشوي again. Spin again. We have 2 to go. ما شاء الله يزن معنا. يزن.
Last one. And let's see who is our final winner for today.
Last one. على ما قال آخر حبة للي تحبه.
David Brooks. Congratulations, David.
Congratulations, everybody.
So just please, whoever got their names popped up, please just send us private message on Teams with your email so we can approach you later on. Or you can email us with your information. Thank you very much. And now we'll move to last session, which is I'll hand it over to you, Abu Abdurrahman.
Allah يجزاك خير. Can you hear me?
Yes.
Okay. حقيقة أول شيء I would like to thank everybody for this event, which is so successful, I believe. With special thanks goes to IMI and the coordination team and the presenters, including Mr. Ahmed Al-Suhaimi and Mr. Christian Buehler and Mr. Sakhar Shami from IMI. And we'll make sure that the appreciation certificate and trophies will be mailed to the IMI team soon. Inshallah, we'll get it to your door. Also, I wanted to inform everybody that ASME Eastern Saudi section will be hosting 2 or 3 events by end of this year, inshallah, including the year end session. And also, I wanted everybody to participate in the Twitter that we have. I'm sure you have a copy of that. And we appreciate your comments and feedback, which we always appreciate to help us keep improving in future events. Everybody just stay safe and have a good one. Wa alaikum salam wa rahmatullahi wa barakatuh.
Thank you.
Thank you.
Thank you.
Thank you very
Thank you
much.
so much.
Thank you,
Bye-bye.
everybody.